Hello everyone, this is Nikhila Tikpannavar from Aryan Arts, Commerce and Science Junior College, Baudan. Today we are going to learn coordination compounds. In last video, we have seen what is meant by coordination compounds, what are the types of ligands, terms used in coordination compounds and Werner's theory of coordination compounds. Now we will see IUPAC nomenclature of coordination compounds, effective atomic number rule, that is EAN rule, and isomerism in coordination compounds. So let's start with IUPAC nomenclature of coordination compounds. There are certain rules for naming coordination compounds recommended by IUPAC. They are as follows. First rule, in naming the complex ion or neutral molecule, name the ligand first and then the metal. The names of anionic ligands are obtained by changing the ending IDE to O and ATE to ATO. So if it is chloride, it will be changed to chloro, or sulfate to sulfato. We will see the examples later on, so you will get more idea about it. The name of complex is one single word. There must not be any space between different ligand names as well as between ligand name and the name of the metal. Next rule, after the name of the metal, write its oxidation state in Roman number, which appears in parenthesis without any space between metal name and parenthesis. If complex has more than one ligand of the same type, the number is indicated with prefixes di, tri, tetra, penta, hexa, and so on. For the complex having more than one type of ligands, they are written in an alphabetical order. Suppose two ligands with prefixes are tetraaqua and dichloro. While naming in alphabetical order, tetraaqua is first and then dichloro. If the name of ligand itself contains numerical prefix, then display number by prefixes with bis for 2 ligands, tris for 3, tetrakis for 4, and so on. Put the ligand name in parenthesis. For example, ethylene diamine thrice or EN3 would appear as tris ethylene diamine or tris ethane 1,2 diamine. The metal in cationic or neutral complex is specified by its usual name, while in the anionic complex the name of metal ends with ATE. The table shows IUPAC names of anionic and neutral ligands. So bromide ligand, we will call it in IUPAC bromo. For chloride, IUPAC name is chloro, fluoride, fluoro, carbonate, carbonato, hydroxide, hydroxo, oxalate, oxalato. So if it is having last ending IDE, we will convert it to O, or ATE is converted to ATO. Sulfate to sulfato, nitro to nitrato. Ammonia, it is named as amine, AMMINE. Water, aqua. Next is IUPAC names of metals in anionic complexes. So if it is aluminium metal, in IUPAC we will write aluminate, cobalt, cobaltate, gold, aurate, manganese, manganate, platinum, platinate, and so on. So see this complex. First is anionic complex. It is NiCN4 2-. So we will write tetra, cyano, nickelate, and Roman 2. So tetra indicates there are 4 cyanoligands. Then metal is nickel metal, so nickelate, and it has a 2 charge, minus 2 charge. So we have written in bracket 2 in Roman. Okay. So next category is compounds containing complex anions and metal cations. So look at this, Na3 in square bracket, cobalt, NO2, 6 square bracket complete. So sodium is outside the coordination sphere, so we will write sodium first, then we will write hexa nitro. Ligand will appear first before the metal atom, so hexa nitro cobaltate, and it has plus 3 because 3 sodium atoms are outside the coordination sphere to neutralize that charge. So we have written in Roman 3 in bracket. Next is cationic complex CuNH3 4 2 plus. So we will write first ligand tetraamine. See the spelling AMMINE, copper and charge 2, so therefore 2 Roman number. Next category is compound containing complex cations and anions. So in this Pt platinum Br2 NH3 4 Br. So we will write first ligand tetraamine, then 2 bromines are in coordination sphere, so dibromo platinum 4. So here bromo and amine. So we will write amine first, as it comes alphabetically, amine will be the first. So tetraamine dibromo platinum 4 and 2 Br2, they are outside the coordination sphere, so we will write bromide. Lastly, neutral complexes. So see this example, cobalt NO2 thrice, NH3 thrice. So we will write triamine trinitro cobalt 3. So in amine and nitro, amine will come first alphabetically. So we have written triamine trinitro cobalt 3. Okay. So you can learn how to write, you should learn how to write IUPAC names of some complexes. Now we will see the effective atomic number or EAN rule. An early attempt to explain the stability of coordination compounds was made by Sidgwick, who proposed an empirical rule known as effective atomic number rule. EAN equals to total number of electrons around a central metal ion in the complex. EAN rule states that a metal ion continues to accept electron pairs till it attains the electronic configuration of the next noble gas. Thus, if the EAN is equal to 18 of argon, 36 of krypton, 54 of xenon or 86 of radon, then the EAN rule is obeyed. The effective atomic number can be calculated with the following formula. EAN is equal to number of electrons of metal ion plus total number of electrons donated by ligands. So we can call this atomic number of metal Z minus number of electrons lost by the metal to form the ion, which is X, plus number of electrons donated by ligand, that is Y. So the formula for EAN will be Z minus X plus Y. Z is atomic number of metal, X is number of electrons lost by metal to form ion, and Y is number of electrons donated by ligands. So see this example, cobalt NH3 6 3 plus. So here oxidation state of cobalt is plus 3, 6 ligands, donate 12 electrons. So Z is equal to what? 27, which is atomic number of cobalt. X, that is number of electrons lost by metal to form iron. So charge is given +3, so X will be 3. Y, that is number of electrons donated by ligands, that is 12. So EAN for cobalt 3 plus is equal to 27 minus 3 plus 12. So it is 36. So EAN rule is obeyed. CrCO6 and FeCN6 4- are some examples of coordination compounds which obey the EAN rule. Certain other coordination compounds, however, do not obey the EAN rule. For example, FeCN6 3- and CuNH3 2+ have EAN 35. Next we will see the isomerism in coordination compounds. It is one of the interesting aspects of coordination chemistry is existence of isomers. Isomers are different compounds that have the same molecular formula. Their chemical reactivities and physical properties such as color, solubility and melting points are different. Broadly speaking, isomers are classified into two types, namely stereoisomers and constitutional or structural isomers. So look at this table. Isomers are divided into stereoisomers and constitutional isomers. Stereoisomers are further divided into geometric or diastereomers and optical isomers or enantiomers. And constitutional isomers, they are further divided into linkage isomers, coordination isomers, ionization isomers and solvent isomers. So we will see one by one isomers in coordination compounds. So we will start with stereoisomers. Stereoisomers have the same links among constituent atoms. However, the arrangement of atoms in space are different. There are two kinds of stereoisomers in coordination compounds: geometric isomers or diastereomers and enantiomers or optical isomers. So we will see first what is meant by geometric isomers or diastereomers. These are non-superimposable mirror image isomers. These are possible in heteroleptic complexes. In these isomers, there are cis and trans type of arrangement of ligand. In cis isomers, identical ligands occupy adjacent positions, and in the trans isomers, identical ligands occupy the opposite positions. Cis and trans isomers have different properties. Cis-trans isomerism is observed in square planar and octahedral complexes. Cis and trans isomers in square planar complexes. The square planar complexes of Ma2B2 and Ma2BC type exist as cis and trans isomers, where A, B, C are monodendritic ligands and M is metal. So see this example: platinum NH3 twice Cl2. It is a type of Ma2B2 type. So platinum is attached to 2NH3 and 2 chlorines. So in cis, both chlorines are on adjacent sides and both amines are on adjacent sides. So it is a type of cis isomer. In second image, we can see both chlorines are on opposite side and both amines are on opposite side of the metal. So it is trans isomer. Here, the cis isomer is more soluble in water than the trans isomer. The cis isomer named cisplatin is an anti-cancer drug, while the trans isomer is physiologically inactive. The cis isomer is polar with non-zero dipole moment, while the trans isomer has zero dipole moment as a result of two opposite platinum chlorine and two platinum NH3 bond. So both chlorines are on opposite sides and both NH3 and H2O, they are on opposite side. So it does not have any dipole moment. So they cancel each other. Dipole moments are cancel each other. Four coordinate tetrahedral complexes do not show cis and trans isomers. Next is cis and trans isomers in octahedral complexes. The octahedral complexes of the type MA4B2 and MA4BC and MAA2B2 exist as a cis and trans isomers, where AA is a bidentate ligand. So see this example, CONH34Cl2. It is a type of MA4B2 type. Look at the cis and trans isomer. In cis, the ligands are on the same side. In trans isomer, they are on the opposite side of the metal. See second example, PTNH34ClBr. It is a type of MA4BC type. Here also we can see the ligands, same ligands are on the same side. So it is a cis isomer. And in second image, we can see the same ligands are on opposite sides. So the dipole moment gets cancelled. So it will be a trans isomer. Same ligands, opposite sides. So trans isomer, same ligand, same side, cis isomer. Now we will see what is meant by optical isomers or enantiomers. The complex molecule or ions that are non-superimposable mirror images of each other are enantiomers. The non-superimposable mirror images are chiral. Enantiomers have identical properties, however differ in their response to the plane polarized light. The enantiomer that rotates the plane of polarized light to right or clockwise direction is called dextroisomer, while the other that rotates the plane of polarized light to the left or in anticlockwise direction is called levoisomer. Octahedral complexes existing as both geometric or optical isomers. See this example, PtCl2 EN twice 2 plus. In this type of example, only the cis isomer exists as a pair of enantiomers. In square palazzo complexes do not show enantiomers, since they have mirror plane and axis of symmetry. Look at this. There are two chlorine and two ethylene diamine molecules. So in cis, two chlorines are adjacent to each other. So we will get the mirror image. So it will be a non-superimposable mirror image of each other. So they are enantiomers. What is meant by non-superimposable mirror image? See this molecule and it is its mirror image. So if I take out this molecule and put it over right side molecule, second molecule, so I am not getting the same type of molecule again. So they are non-superimposable mirror images of each other. So they are enantiomers. But look at this trans isomer. It has two chlorines are opposite side and ethylene diamine molecule also on opposite side. So if I put a mirror uh, beside this molecule, I am getting the same geometry as that of this isomer. So they are superimposable images of each other. I am getting the same molecule again. So they are not enantiomers of each other. Have you understood? Next is structural isomers. or constitutional isomers. Structural isomers possess different linkages among their constituent atoms and have their chemical formulae to be the same. They can be classified as linkage isomers, ionization isomers, coordination isomers, and solvate isomers. First, we will see the linkage isomers. These isomers are formed when the ligand has two different donor atoms. It coordinates to the metal via different donor atom. Thus, the nitrite ion NO2 having two donor atoms show isomers as follows. Look at this example CONH35NO2 2 plus and CONH35ONO 2 plus. The nitro complex has CO N bond, that is cobalt is connected directly to nitrogen bond, and in nitrito complex is linked through cobalt, it is linked to oxygen. So they are linkage isomers. Next is ionization isomers. Ionization isomers involve exchange of ligands between coordination and ionization spheres. For example, cobalt NH35SO4 Br and cobalt NH35Br SO4. In compound 1, anion SO2 bonded to cobalt, it is in coordination sphere, while bromine it is in ionization sphere. And in compound 2, anion bromine is in coordination sphere linked to cobalt, while SO2 is in ionization sphere. So these complexes in solution, they will ionize to give different ions. So first compound will ionize CONH35SO4 Br, it will ionize to give CONH35SO4 plus Br minus. And second compound CONH35Br SO4, it will ionize to give CONH35Br 2 plus SO4 2 minus. So first and 2, compound 1 and compound 2, they are examples of ionization isomers. Next is coordination isomers. Coordination isomers show interchange of ligands between cationic and anionic spheres of different metal ions. For example, cobalt, amine 6, chromium CN6, chromium amine 6 and cobalt CN6. In isomer 1, cobalt is linked to amine ligand and chromium to cyanide. And in isomer 2, the ligands coordinating to metals are interchanged and cobalt coordinates with cyanide ligand and chromium to amine ligand. So compound 1 and compound 2, they are examples of coordination isomers. And lastly, the solvate isomers or hydrate isomers when water is a solvent. These are similar to the ionization isomers. Look at these complexes CrH2O6Cl3 and compound 2 will be CrH2O5Cl Cl2H2O. In compound 1, the solvent water is directly bonded to chromium, and in compound 2, H2O appears as the free solvent molecule. So compound 1 and compound 2, they represented solvate or hydrate isomers. Thank you everyone.